Well, we'll get started again here. One might ask, why did I draw it like this? Why didn't I draw it like this? If I'm going to draw oxygen as the center, why didn't I put the hydrogens on there as well, like this? Do you see why I didn't do this? Can you see why I didn't do this? And then, okay, I have 2 hydrogens, and then I have 2 more. So put 2 here like this, 2 here like this. Well, one problem is, yeah, carbon would be left without an octet, but we would have, let me see how many we'd have left over. How many have we used? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now it looks good, right? Does this look good? No. This doesn't, why doesn't this look good? Everything has an octet. Oh, I'm sorry, can you repeat that?
Would it be because the hydrogens at top and bottom would be close to each other?
No, they could be close to each other, it's fine. Well, when we draw Lewis structures, we don't care about the shape. We just try to link things together. That's it. Uh-huh. Yeah, what would the formal charge on carbon be? Two, 3, 4, 5, which means this should be negative. And so the formal charge on this carbon is going to be negative. What about the formal charge on this oxygen? This one would be +2, and then this carbon would be negative as well. And so do you see why this structure doesn't look good? Yeah. This structure doesn't look good even though everything has an octet. It just doesn't look right. And that comes from experience, because I've drawn a lot of these structures, and then what we see from experience is we see different bonding environments. So for example, here, we can take a look at just carbon itself. If I look at carbon, there's something called organic chemistry. And organic chemistry is based on the chemistry of carbon, basically. It's based on the chemistry of carbon because carbon can bond in a lot of different ways. So for example, carbon can have 2 groups, like that, like in CO2. Although CO2 is not considered an organic chemical, do you know CO2 is called an inorganic? So typically with the organic chemicals, we have carbon and hydrogen. And that could be oxygen, like ethanol, carbon, hydrogen, oxygen. Dimethyl ether, carbon, hydrogen, and oxygen, etc. Okay, but carbon likes to form a total of 4 bonds in different arrangement. So we could have something like this, where it's 180 apart. We call this 2 groups. Your lab doesn't call them groups. You know what your lab calls them? They don't call them pairs. They call them sets. And so this would be 2 sets. Now carbon can also have 3 sets, except one of those has to be a double bond. Otherwise, the formal charges are going to get all screwed up, right? Or if it did have something like this, it could have a lone pair and 2 single bonds, but it's going to have a negative charge on it. Something like that. And so that could screw up, the formal charges get all screwed up. Now carbon can have 4 bonds, like this. When they have 4 bonds, we try to draw it 3-dimensionally. So we'll try to draw 2 of the bonds in the plane, like this, and then 1 coming out and 1 going in. So let's build this one here. Now carbon's black, so if you could take a black one and then just put 4 sticks into a black ball. The short or long sticks, but just have the same size stick.
Long sticks or short sticks?
Just do the 4 long sticks to that. It doesn't matter. If you did short, it's fine. Short or long. Do you see that? That's called tetrahedral. A tetrahedral arrangement of groups. Not a tetrahedral arrangement of atoms yet. Do you see, can you draw it or can you orient it on the page so it's like this drawing? Two in the plane, one sticking out, one going in. It's called the wedge dash drawing. So are you good with that? Can you visualize it? Now, the same thing, you know, when we look at oxygen, we have different scenarios for oxygen. Oxygen can have 4 groups, 2 lone pairs and 2 bonds like this. Or oxygen can have 1 double bond. Oxygen likes to form how many bonds? 2 bonds. But sometimes oxygen will form 3 bonds. If oxygen forms 3 bonds and it has 1 lone pair, the charge gets screwed up. What does the charge become? It becomes positive. An example of this would be this ion. This ion is going to have a positive formal charge on the oxygen. And we call, do you know the name of this ion? H3O+. This is called hydronium. And so sometimes we'll see this kind of bonding environment for oxygen. How about nitrogen? Nitrogen likes to form how many bonds? 3 bonds. 3 bonds. And so here, 1, 2, 3, and then we'll have a lone pair. This one would be which one? Scenario A, B, or C? If it has 3 bonds and 1 lone pair, is it A, B, or C? It's C, you know. 3 bonds, and then this should be converted into a lone pair. And that gives us 4. And so it's going to adopt this type of tetrahedral set geometry. We could also have 4 bonds. If we have 4 bonds to nitrogen, then the nitrogen is no longer going to be neutral. The nitrogen is going to have what charge? We saw this yesterday, yeah. It's going to have a positive charge. Or the nitrogen can have a double bond and a single bond. If it has a double bond and a single bond, what's the charge on that?
Positive. No, negative.
This would be neutral. It would be 0. Or it could have 2 single bonds and 2 lone pairs. If it has 2 single bonds and 2 lone pairs, then it's negative. And so we see different ways that these atoms can link, and then what you have is you have those in your mind so you can kind of come up with different scenarios. When we look at fluorine, there's only one arrangement for fluorine, and that's this. This fluorine hates this. Do you know why fluorine hates this? Let's say I try to make a double bond with fluorine. It hates it because what does that do to the formal charge on fluorine? Remember, we're going to split the bonding electrons in half. 1, 2, 3, 4, 5, 6. How many does fluorine have? 7. So this makes it positive. Is fluorine happy being positive? No. Fluorine never forms double bonds. Fluorine will not form double bonds. Does not double bond. Not double bond. And so I have these kind of blocks, you know, that help me figure out potential structures. So we call this one linear. If I have 2 groups, those 2 groups try to stay apart from each other. This is 2 balloons. The furthest we can separate is a 180-degree angle. It's a linear. This is electron pair geometry, EPG. EPG is linear. Again, pairs of substitute set for group for that. If I have 3 groups, then we have what's called trigonal planar. EPG, trigonal planar, 120-degree angle between the balloons here. Now if I put a fourth balloon, the fourth balloon is going to go on top, pushing these three balloons down. So I put in the fourth balloon on top, pushes those three down, and this becomes tetrahedral, EPG tetrahedral. What's the angle? The angle between any two balloons is 109.5, even though it doesn't look like it. You pick any two balloons, even these two look opposite each other, but the angle is the shortest angle, which would be 109.5, the smallest angle. Those are the EPGs, but we're not interested in the EPGs ultimately. We need the EPGs to help us figure out the geometry, but what we're interested in is the MG. The MG is the molecular geometry. The MG. And so let's take a look at this one, this ABA. This ABA molecule has no lone pairs, just two groups. Those two groups are going to orient 180 apart from each other. And so the EPG just looks at the groups. The MG looks at the atoms. And so for CO2 would be like this. The EPG looks at the groups. So we have two groups. And so the EPG is 180, or linear. 180 degrees. The MG looks at the atoms. And so the molecular geometry, the MG is going to look at the atoms. The atoms are going to be in the same orientation. And so the MG is linear, 180 degrees for the atoms. If we have three groups, then it's going to adopt the trigonal planar group geometry, so three groups. And if the atoms are oriented in the same arrangement, then it's going to adopt the trigonal planar molecular geometry. Look at the atoms. We could have a double bond, a lone pair, and a single bond like this. This would be three groups. Three groups. Lone pair is not really seen here. But here's where we're going to have a difference between the EPG and the MG. The EPG is trigonal planar, however the MG is not. The MG is this. It's called angular or bent, or in the video they called it the V shape. So angular, bent, or V shape. That's because we're just looking at the atoms for the MG. For tetrahedral EPG, there are three possible scenarios for the atoms. One, we could have a tetrahedral arrangement of atoms. Two, we could have a trigonal. What's this one? Like ammonia. Ammonia we call trigonal.
Pyramidal.
Yeah. Or three, we could have a V-shaped or bent or angular shape, like in water. Water will have four groups, two lone pairs, two bonds. Two lone pairs we don't see here. We just see the atoms here, which is bent or angular for the MG. So all three of these have the same EPG. Methane, EPG's tetrahedral. Ammonia, EPG's tetrahedral, because here we have four groups. Single bond, single bond, single bond, lone pair, four groups. So EPG's tetrahedral. Here, water, EPG's tetrahedral. Single bond, lone pair, four groups, tetrahedral. But the molecular geometries are different. Tetrahedral, trigonal pyramidal, and bent or angular. Okay, let's take a look at this fluorine here. The fluorine, what would the EPG around fluorine be? Tetrahedral. And since this has got to be linear, though, because there's only one atom bonded to it. Right. This carbon, what's the EPG on the carbon? trigonal planar. What's the Mg around the carbon? Trigonal planar, because the atoms, we've got a fluorine, fluorine, carbon, they're in the same arrangement. And it's mirrored here. Polarity is not part of this lab. We're gonna stop here, and we're gonna take a look at the lab now. I don't think we're doing polarity. No, we're not. Okay, so the lab is exercise B, and let me switch over here. Okay, we'll do the first few together and then set you off on your own. First molecule is ammonia. We already did that. The number of valence electrons, 8. The central atom, nitrogen. The sets, how many sets around nitrogen? Or how many groups of electrons around nitrogen? And so we have to have the Lewis structure to figure that out. And so this is the Lewis structure we generated for ammonia. And so how many groups of electrons? 4. And what are they? We have 3 bonding groups and 1 lone pair. And so there are 4 sets. 3 bonds, 1 lone pair. BA. I don't know what the A is. So if we have 4 groups, we're going to build this. Nitrogen's blue, so go ahead and build this one. Well, we're going to do hydrogen's white. So can you build it? And then what we're going to do is we're going to orient it like this. Use a short stick for the lone pair. Use a long stick for the single bond. Okay, can you tell me what the angle is between any 2 sticks? 109.5. Okay, that's what we call the ideal ideal angle. 109.5. But what's the geometry of the what is the EPG? Tetrahedral. Tetrahedral. But when we look at the molecular geometry, what is the Mg? Trigonal pyramidal, just the bonded atom. Okay. Now the last thing is this. Do you expect any distortions to the bond angle? Okay, what they mean by that is this. What they mean by that are if all 4 groups are equivalent, then there should be no distortions. It should just be a perfect tetrahedral arrangement of groups, right? But all 4 groups are not equivalent. As far as the electron cloud goes, in a bond, the electron cloud is being pulled between 2 atoms. There's a tug of war for the electron cloud. Which atom is going to win? Nitrogen or hydrogen? Nitrogen. And so it's going to be, but is hydrogen going to be a complete loser?
No.
No. And so the electron cloud is polarized towards nitrogen, which I drew just as a circle here. That should be a blue circle. On nitrogen, we just use a blue ball. Now, what's happening with the lone pair? The lone pair, is there a tug of war for the lone pair? You know what? There's no tug of war. Nitrogen is going to have an easy time with the lone pair. And so that means the nitrogen can pull the lone pair in very tight. If it pulls in the lone pair very tight, like this, then what that does is it concentrates the electron density more than out here. And so in other words, it makes a more dense negative charge region here. If there's a more dense negative charge region here, then what that does is it pushes these three groups away. And these three groups get pushed down because of the higher negative charge density. Higher negative charge density. Still 2 electrons, but it's just more dense. Since more dense is more negative. More negative is going to push these other ones down. If it pushes these other ones down, it distorts the angle. And so these three get pushed down. So normally it's supposed to be a 109.5 angle, and it gets distorted to about 107 degrees by being pushed in. Does that make sense? And so what we're going to do here for the bond angle is we're going to say the bond angle is going to be less than ideal. The bond angle. Now bond angle is defined by 3 atoms, so it's the HNH angle is going to be, it should be 109.5, it's going to be 107. Roughly 107.5. All right, now we'll do the molecular geometry drawing. That's this. This is the Lewis. This is the MG drawing. The MG drawing, you're going to do this. You're going to draw the lone pair and this bond in the plane. This bond's going to stick out, this bond's going to stick in. Can you orient your model on so it matches your drawing on paper? Okay? Did you guys draw? Uh-huh. The set geometry is, what is it? Or it's tetrahedral in this case? It's the group geometry, or the EPG, electron group geometry, electron pair geometry. And this is it. The set geometry just looks at the groups. 1 group, 2 groups, 3 groups, 4 groups. If you have 4 groups, it's like this. 4 sets, it's tetrahedral. 3 sets, it's 3 sets equals trigonal planar. 2 sets equals linear. So the first thing we do is we look at how many sets there are. We'll just count it. Okay, I'm going to skip PCl4 plus and let's look at NOCl. NOCl is called nitrosyl chloride. And what should we put in the center? The formulas may or may not tell you what goes in the center. We can't always tell what goes in the center by looking at the formula. Because if you look at the formula, remember this formula, HCO3 minus? Is this hydrogen even bonded to the carbon? No, but why did they write the formula like this? They wrote the formula like this because they don't care what goes in the center. And, you know, it does. And so don't use this to automatically, so if we have something like this, NOCl, which atom usually goes in the center?
Nitrogen.
Yeah, it'd be less electronegative. The nitrogen would go in the center. But not always, because oxygen is perfectly happy as well being in the center. But you have to be careful. Because normally we would think nitrogen goes in the center, but maybe not. Maybe oxygen goes in the center. And so let's try drawing this one out together here. If we try drawing this one out, NOCl, I kind of think oxygen goes in the center because of the way they wrote it, but I don't want to be deceived, you know? And so what I'm going to do is I'm just going to go through my usual procedure. Usual procedure is nitrogen has how many? 5. Oxygen?
6.
Chlorine?
7.
12, 18 electrons. And then I'm going to put the nitrogen in the center here because usually we put the least electronegative in the center. And then I have 2, 4. So let's go with oxygen. Oxygen's more electronegative than chlorine, so oxygen is going to get its electrons first. And so that takes care of 10. And then chlorine, we'll take care of chlorine next. And that takes care of 16. And then we have 2 electrons left over. We'll put those on nitrogen. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. 18 electrons. So does this structure look good? No, it doesn't look good. And so I go, well, why doesn't it look good? The nitrogen is missing an octet. So I have 2 choices. The oxygen can make the double bond or the chlorine can make the double bond. What do you think prefers to form 2? Oxygen prefers 2 bonds. Chlorine likes just to form 1 bond. Otherwise it screws up the formal charge. But chlorine can make more than 1 bond. You know, if chlorine makes 1 bond, it has 0 formal charge. If chlorine makes 2 bonds, then the formal charge goes to +1. If fluorine makes 3 bonds, it could be 3 single bonds, you know, or 2 whatever. Then it's going to screw up. So what we'll do is we'll take 1 pair from oxygen and make a bond here. Now does everything have an octet? Yeah. Okay, so this looks okay. 2, 4, 6, 8, 10, 12, 14, 16, 18. Next, we ask this. What are the formal charges? Zero, zero, zero. That's good. That structure looks good. Right? That's a good structure. What if we put the oxygen in the center? Let's just put the oxygen in the center and see, because oxygen doesn't mind being in the center at all. We see it in the center in so many different compounds. And so let's try to put oxygen in the center. So we'll go NOCl. NOCl like that. All right, then we're going to complete it. Nitrogen versus chlorine, which one will get its electrons first? Which one's hungrier for electrons?
Chlorine. No. Nitrogen.
Well, it depends on electronegativity. I think probably which one's more electronegative? It turns out that nitrogen happens to be a little bit more electronegative. The three most electronegative elements are nitrogen, oxygen, and fluorine. And so we'll complete nitrogen first, although that's hard, you know. And then we'll complete chlorine, and then we have
Oxygen.
oxygen with a pair like that. Okay, does this structure look good? No. Yeah, so let's try to fix that. I'm going to take a lone pair off nitrogen and give it to oxygen. We end up with this. Okay, does this look good? Yeah, octet looks good, but what about the formal charges? Do you see the funny bonding? The funny bonding, N has 2 bonds and 2 lone pairs, and it's going to give it a formal charge of? Well, it has 6. Well, no, it does
Plus.
2, 4, 5, 6.
Or sorry, minus.
Minus, yeah. It's going to have minus. This oxygen looks funny too, because normally oxygen likes to form how many bonds? It likes to form 2 bonds, but in this case it's forming 3 total bonds. 1 double, 1 single is 3 total bonds. And that means its charge is going to be?
2, 4, 5. Plus.
Plus. How about this chlorine?
2, 4, 6, 7. Plus. No, chlorine's good.
Chlorine's 0.
0.
So between these two, which is better?
That one, first one.
This one is better. Do you think oxygen is going to lose an electron to nitrogen? No, not if it can help it. Sometimes it can't help it, though. And so let's go down nitrosyl then. Number of valence electrons? How many did we have? 18? No. 18? Was it 18 or was it? Oh, 18 is yes. 18 valence electrons. What's the central atom? Nitrogen. How many sets? We have 1. We can't split this, so this is 1, 2, 3. 3 sets. 3 sets. 2 bonding sets and 1 lone pair. What's the set geometry? No. No. Trigonal planar. We have 3 sets. We got to separate those 3 sets as far apart as possible. So 1 set is the lone pair, and then 1 set is the single bond. The other set is a double bond. And so 3 sets. 1, 2, 3. Trigonal planar would be the set geometry. If I adopt the trigonal planar set geometry, what's the ideal angle between the sets? 120. 4 sets would be 109. 3 sets is 120 because we call this trigonal planar. Trigonal planar. It's the ideal bond. Now the molecular geometry, we've got to draw the molecular geometry next. The Lewis structure does look linear, but it isn't. Since we got to draw it, we'll draw 1 set up here, and then 1 set will be distorted down here. We keep the sets as far apart as possible, and then the double bond will be out here. Like this. Turns out double bonds are shorter. And so we could make this. You know, we'd have to use the brown or brown one, and brown one has 5 holes in it. But we just have to pick the 3 that are like this. We'll use a short stick for the lone pair, a short stick for the double bond, and a long stick for the single bond. Double bonds are shorter than single bonds. And so maybe I should draw it like that as well. And so you need the brown one, and then there are 2 holes opposite each other. You hold those with your finger, and then there are 3 holes that are at 120. You guys got it? It should be flat. Is it flat? Yeah, good. Now, the set geometry is trigonal planar, but the molecular geometry is bent. And so the molecular, we don't have to use any wedges for this. We'll just lay it flat on the page. That should be fine. Okay, what about the last entry says that the bond angle. The bond angle is the ONC angle. We usually write it like this. ONCL angle should be less than 120, equal to 120, or greater than 120. About, you know, because we have two factors affecting this. This lone pair is going to try to push them together, right? And so this lone pair tries to push them together, but the double bond is that. And so the space requirements go like this. The lone pair requires the most breathing room, the most space, followed by the double bond, followed by the triple bond. But, you know, it's not a huge difference. So what we're going to just say is it's about 120 because the distortions are going to cancel each other out. Does that make sense? Just guess about 120. Do you want to go through more together, or do you want to start working on your own? I'm sorry, more together, or start working on your own? More together? All right, let's do PCl4 plus. PCl4 plus. Phosphorus, how many valence electrons? 5. And then we have 4 chlorines. Each chlorine is 7, so 4 times 7. And then, oops, we have a charge. A +1 charge means we take away electron or add an electron? Take away one. And so 4 times 7, 28. 32, so right, 32 electrons? 32 electrons total. Okay, what should we put in the center? Phosphorus. So this seems probably put phosphorus in the center and then 4 chlorines. Chlorines just like to form one bond if at all possible. That takes care of 2, 4, 6, 8. And so what we'll do is we'll just try to complete the octets to the chlorines by adding 3 lone pairs to each. 3 lone pairs. And so what we have here, we got 2, 4, 6, 8. 8 times 4 is 32. This is 32 electrons. So we're good. This whole thing carries a positive charge. Where does this positive charge originate from? Well, let's take a look at the formal charges. Formal charges here. What's the formal charge on chlorine? 0. Well, each chlorine is 0. We've got 2, 4, 6, 7. It's supposed to have 7. How about phosphorus? How many does phosphorus have? It's supposed to have 5. Does it have 5 in this structure? No, it has how many? 4. It's short 1. If it's short of 1 electron, it's going to have a positive deficit. So the positive charge originates from the phosphorus here. Okay, now let's just look at the phosphorus. How many groups of electrons around phosphorus? Well, I got a single bond here, single bond, single bond. 4 single bonds, so that's 4 groups. 4 sets or 4 groups equals 4 sets equals Tetrahedral, trigonal planar, or linear? Tetrahedral. So the EPG is tetrahedral. Okay, so what we'll do is we'll start the molecular geometry drawing here. We know the EPG is tetrahedral, so we'll put the phosphorus in the center. And this is how we draw the tetrahedral. You could use a black or a blue one for this. We'll put one single bond in the plane going straight up, one single bond in the plane going down at an angle of 109.5, one single bond coming out as a wedge, and one single bond going in as a dashed line or dashed wedge. Can you guys build this?
Yeah.
And then for chlorine, we use green. So we see the EPG is tetrahedral. And now when we add the atoms, we'll put a green chlorine on here, another green, a ball here for chlorine. The halogens are green. Another one here, another one here. So we see we have an EPG of tetrahedral, and then the MG, the molecular geometry, is going to be tetrahedral. Well, what is the ideal angle for tetrahedral? 109.5. But do you expect any distortions on this? No, because all the groups are the same. They're all single bonds. All single bonds are about the same. And in fact, these are exactly the same. And so the ideal angle and the bond angle should be the same. Bond angle should be 109.5. Okay, are we good? Uh-huh. Oh. Now, what do they mean by the lone pairs here? The sets are, we have to take each of these atoms one at a time. And so the phosphorus, does the phosphorus have any lone pairs? No, so it just has 4 bonds. BA stands for bonded atoms, but anyway, there are 4 bonds here, no lone pairs. However, chlorine has 3 lone pairs and one bond. But we don't have a box for chlorine. We'd need a second box here for chlorine. Because chlorine's a terminal atom. All terminal atoms are always linear. Because there's only one thing bonded to it. And so all terminal atoms are always going to be linear no matter what they are. And so we don't analyze the terminals yet. We only analyze the central. If we have more than one central, then we'll need a box, another box to do that. In fact, let's take a look at this one. We're going to look at H2SO4 next. We're skipping nitrite for now. We'll come back to it. Which atom should we put in the center? Sulfur. Okay, then we'll just put 4 oxygens and 2 hydrogens to it. Does that look okay to you, or does it look off a little bit? It looks off because sulfur is going to have more than an octet, and so let's see if we can avoid having more than an octet on sulfur. In fact, let's do it like this. We'll put sulfur here, and then what we'll do is we'll put the oxygens like this, and then we'll put hydrogens like this. How about that? Does that look better? It looks better. But how many electrons do we have? So we have 2 hydrogens, that gives us 2 electrons. 1 sulfur has how many electrons? 6. 4 oxygens, that's 4 times 6. There's no charge. So 24, 30, 32. 32 electrons again. How many have I used? 2, 4, 6, 8, 10, 12. And so let's complete the octets to the oxygens. 14, 16, 18, 20, 22, 24. I still have more electrons left over. 26, 28, 30, 32. So I can complete the octets here to the oxygen. Except one thing's going to look funny, and that is the formal charges. Let's take a look at the formal charges here. What are the formal charges? Okay, this hydrogen is 0. This oxygen is 2, 4, 5, 6. Gave 6, 0. This sulfur has 1, 2, 3, 4. How many did it give? 6. If it gave 6 and ends up with 4, then its deficit is plus 2. And so this sulfur is actually going to be kind of high. It's lost 2 electrons, plus 2. Where did those electrons go? The oxygen. This oxygen is going to be minus 1. This oxygen is going to be minus 1. Okay, and these are 0, like that. And so the formal charges are kind of high. Do you see that? Kind of high. Can we get rid of those? Well, one thing we could try is we could try a different skeleton, maybe like this. If we do that, then let's complete the octets to the oxygen first. How many electrons does that take? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. 28, 30, 32. 32. All right, let's take a look at the octets. Are the octets good? This is the first thing we always look at, the octet. Yeah, the octets are good. Formal charges. All the formal charges are 0. So based on this, which structure looks better? Yeah, the second one looks better. But this is something you have to have memorized. Oxygen, unlike carbon, hates to bond to each other by a single bond. That's called a peroxide bond. This is a peroxide bond. This is also a peroxide. Peroxide bonds are okay. There's a whole class of organic chemicals called peroxides, and they all have oxygen-oxygen single bonds. But what is one of the chemical properties of peroxides? You might have a bottle of hydrogen peroxide at the house. What do you know about hydrogen peroxide? Is it stable or not so stable? That's a bottle of peroxide. Self-ignition. Stable? No. That's what we know about peroxide. Although hydrogen peroxide is okay, organic peroxides are not. Because organic peroxide,
These containers were enough. They were, in fact, allowed to reach the self-accelerating decomposition temperature. Or
they just got a little bit too warm. You got to keep peroxides in the freezer. And so we do have some peroxides. We store them in the freezer. Because if they get too warm, this is what's going to happen. Basically, they're going to start to decompose. And if they start to decompose fast enough, you're going to get an explosion. Fortunately, the peroxide you have at home is very dilute. It's like, it's pretty dilute. If you had 50% peroxide, you're looking at something quite dangerous. And so, even though this structure looks great, what do you know about hydrogen peroxide? Peroxides are unhappy because oxygen's in the minus. It's not because of the formal charge. It's because of the oxidation state. When you look at the oxidation state, what's the oxidation state of this oxygen?
0.
No. The oxidation state. Oxidation state is winner takes all. So what's the oxidation state on this oxygen here? 2, 4, 6,
6.
and then it has a 7th there. So it's -1. What oxidation state does oxygen like? No, oxidation state, it doesn't necessarily like 0. It likes -2. Think oxygen versus water. O2 versus water. O2 is 0, water is -2. What's more stable, O2 or water? Water. So remember, this is apples versus oranges. We have to compare, apples with apples and oranges with oranges. And so we can't get the numbers mixed up. So all of a sudden I shifted my thinking. When I'm thinking about oxidation states, I automatically shift to the next reference frame. When I'm thinking about formal charges, I'm thinking about something else. There's two different ways of visualizing. But anyway, this looks great, except we have to know oxygen hates forming bonds like this. These bonds are not stable. Carbon loves forming bonds like this. This is why you get long chains of carbon, but you never see long chains of oxygen. Long chains of oxygen just don't happen. Otherwise, it'd be two organic chemistry. One organic chemistry for carbon, one organic chemistry for oxygen. But oxygen doesn't. And so we don't have to worry about separating out another. And so it looks like, you know what? It looks like we're stuck with this. We're stuck with it. We're stuck with that, but you might you might go to Wikipedia or something and then take a look. At the structure of sulfuric acid, and you might notice something funny. What's funny about that structure?
It's a lot.
They have some double bonds. Do you see that? The double bonds. And so what did they do there? What they did is this. This structure is fine. I mean, this structure has an octet, but the formal charge is a little high. Let me get rid of this structure. Is it okay to get rid of the peroxide? Because we don't, if you have a bottle of sulfuric acid, I'm not going to worry about it doing that. But what happens here is this. The sulfur is really lacking. in electron density. And so that's going to make the sulfur more electronegative than it normally is, right? You know, positive 2 charge is going to make it much more. And so what's going to happen is it's going to suck or pull the electron cloud off that oxygen. If it does that, in other words, the oxygen is going to share some of that electron density with sulfur. So what results is something like this. Do you see what happened here? Now look at the formal charges. The formal charges are all 0. But what we have in here is we have an expanded octet. What we call an expanded octet. This is expanded octet is only possible for third and higher periods, the rows. Not possible for second period. Second period is nitrogen, oxygen. Would I ever expect to expand the octet of oxygen? No. Just only for the bigger atoms, I might expect to expand the octet. And so in this structure, we have 0 formal charges, but we have an expanded octet. And so what we say is the formal charge is minimized, but expanded octet. And so we'll just draw the second Lewis structure there. It's the expanded octet Lewis structure.
Where did you write?
Here? Or where?
That's in the F.
Up here?
Yeah.
Okay. FC minimized, but we had to expand the octet in order to minimize it. And so FC minimized, but expanded octet. So this is what we're going to do. We're going to look at the 2 central atoms. First, we're going to look at the sulfur here. If we look at the sulfur here, how many sets do we have? 4 sets. This would be 4 sets, and the 4 sets would be 4 bonded atoms, 0 lone pairs. If we have 4 sets, what's the geometry? Tetrahedral. What's the ideal bond angle for tetrahedral? 109.5. What's the molecular geometry? The geometry of the bonded atoms? Tetrahedral. And then is that bond angle distorted? Well, let's take a look. It's not really distorted because, you know, one double bond pushes it one way, the other double bond pushes it back the other way. And so they kind of cancel each other out. Not perfectly, but so I'd say close to 109. Let's draw the molecular geometry drawing. Now the molecular geometry drawing, we're going to draw it like this. I'm going to draw the sulfur here in the center. And then the way I want to do this is this. I want to do these bridging. These are called bridging oxygens. You see, because they form a bridge. These are called terminal oxygens because they terminate. I'm going to put the two bridging oxygens in the plane of the board. That will make drawing the oxygen geometry a little bit easier. And so here, oxygen. That means the terminal oxygens, one terminal oxygen should be a wedge out, correct? And so one terminal oxygen is going to wedge out, and it's going to have a double bond. And so I'm going to draw two wedges like this. And so I have one oxygen coming out. The other oxygen is going to wedge or dash in. And so I'll draw two dashes going in for the other oxygen to indicate that that's double bonded as well. And so you could make this. Make two long sticks for the single bonds, two short sticks for the double bonds, and then orient it like this. You have it? Red is for oxygen. For sulfur, either use a blue or a black for sulfur. But you could use red for oxygen. Double bonds are going to be shorter, so use the short stick. Single bonds are going to be longer. Use the long stick. Do you have something like this? Okay, now if one of these pushes it down, well, actually both of them are going to push it down. We could see some distortion here, but we aren't going to worry about it. We'll just say about 109. And cancel each other. Okay, can you draw it like this? All right, good. Now let's go to oxygen. Central atom oxygen. How many sets? Okay, we're looking at the bridging oxygen. How many sets? We're on the bridging oxygen. 4 sets. Good. How many bonded atoms? 2. How many lone pairs? 2. Set geometry? Tetrahedral. Ideal bond angle? 109.5. Okay, now the way I'm going to draw that is like this. And you can tweak your molecule like this. So what we're going to do with this molecule is I'm going to draw the bond to the hydrogen in the plane. And so what I'm going to have is I'm going to have the hydrogen, oxygen, sulfur, oxygen all in a plane. So you can twist it. So attach a white ball to your red ball here, and then twist it. Twist it so that the hydrogen, oxygen, sulfur, oxygen are flat. And so what that means is that one lone pair wedges out. And that one lone pair that wedges out, I'm going to draw as solid dots. And then one lone pair is dashed in. I'll draw those as dashed. And so this is my tetrahedral. I have 2 in the plane, 1 sticking out, 1 going in. Tetrahedral, 2 in the plane, 1 sticking out, 1 going in. Do you guys see that? The lone pairs, the red balls only have 2 holes, right?
Yeah.
And so we can't put the lone pairs in there, but you got to imagine the lone pairs are like that. Okay, now we're going to do the same thing for this one. We're going to twist it so that the hydrogen goes like this. And then one lone pair sticks out like this. And the other lone pair sticks in like that. Now, when we think about this, the set geometry, or the EPG, is tetrahedral. What is the molecular geometry here around oxygen? Just the atoms. We're just looking at the atoms. HOS forms what type of geometry? Trigonal planar would have 3. It's bent. It's not linear. Linear would be 180. It's kinked. It's kinked because of these balloons here. And so we call this bent or angular. And the HOS angle should be 109.5, but the lone pairs, remember the lone pairs, concentrate the charge. If the lone pairs concentrate the charge, what's it going to do to this angle here? It's going to push it in. Now, one lone pair is going to push it in about 2 degrees. The second lone pair pushes in another 2 degrees. And so the angle here is about 105 degrees, distorted. This is like water. If we look at water, water is a tetrahedral. EPG, but it's an angular or bent MG. And the bond angle, the HOH bond angle should be 109.5, but it's 104.5. So it's about a 4-degree distortion. Ammonia is about a 2-degree distortion. So we just come up with a general guesstimate, and the guesstimate is that a lone pair is going to cut the angle by 2 degrees. And so that's the 2 lone pairs here cuts the angle in by about 2 degrees. So this angle is about 105, which means it's less than the ideal. Is that okay? The same thing goes here. If I have a double on here and double on here, that's going to compress this angle. And so the OSO angle should be about 105. Yeah. And so actually both these angles are distorted. Now how many lone pairs do I have on the oxygen? I'm not going to do these 3D. I'm just going to put the 2 lone pairs on the oxygen like that. So we have this structure. So did you build this molecule here? Where the HOSOH is flat. Now an interesting thing happens is there's rotation. We call it bond rotation. And so another thing that can happen is the bonds can rotate with kinetic energy. And so the H actually pops out. The H is like a propeller, and it's just rotating around this. You know that? It's kind of interesting. Okay, let's do, I'm going to jump around and then we're going to come back to some of these, or even have you do. Let's do methanol next. Methanol has how many carbons? 1. And in organic chemistry, an alcohol is a COH structure. And so methanol is a CH3OH. Organic chemists try to give as much structural information in the formula as possible. And so when we do this, there are different ways we could do this. Well, one is we can just know carbon likes to form how many bonds? 4. It might not be all singles. It could be 1 double, 2 singles, whatever. But let's see if we can link it all together. So we'll just link the atoms right now. So this carbon to oxygen, and then the oxygen is going to go to a hydrogen. So this is the alcohol part of methanol. All right, and then let's add the hydrogens on here. And then we get CH3OH. And then we have to get a octet around this oxygen, like this. And so this is one way of drawing organic structures. Just figure it out like that. Or we just do it our standard way. Carbon is 4. 4 hydrogens is 4. 1 oxygen is 6. So that gives us 14 electrons. 2, 4, 6, 8, 10, 12, 14 electrons. It checks out. So 14 electrons, 14 electrons. So this would be the Lewis structure. And then what we're going to do is we're going to look at the geometry around carbon, oxygen, and that's it, carbon and oxygen. And so first let's go to carbon. How many sets? 4. And there's going to be 4 bonded atoms, no lone pairs. What's the set geometry? Tetrahedral. And so this is the way I'm going to draw it. What we want to do is we want to draw the chain down and right. And so this would be the chain. or the bridge. The terminals we can draw other ways. Okay, so this is the geometry around the carbon here. What's the ideal bond angle? The HCH angle? 109.5. 109.5. You know, I don't expect any distortions to this because they're all single bonds. And if there is a distortion, it's going to be a very small distortion because this is oxygen versus hydrogen. But since they're all single bonds, I'd say the bond angle is going to be about 109. What is the molecular geometry? The geometry of the bonded atoms. Is the geometry of the bonded atoms the same as the set or group geometry? Yeah. And so it'd be tetrahedral as well. Okay. All right, let's switch over to oxygen. Oxygen has how many sets of electrons? 4. So it'd be tetrahedral as well. And so I'm going to draw it over here. Now for the tetrahedral, I draw 2 in the plane. And so the 2 in the plane I want to draw are the bonds. And so I'm going to make this like this. So this is going to be in the plane. That means one lone pair sticks out, which I'll bolden, and one lone pair sticks in, which I'll dash. So can you visualize that? What I'm looking at, if you can't visualize it, this is what I see on the oxygen. What I see on the oxygen is like this. 2 in the plane, and then 1 sticking out as a wedge like this, and 1 sticking in as a dash like this. Do you see that this is tetrahedral as well? And so this is what I'm seeing here, except this wedge is a lone pair, this dash is a lone pair. This is a bond, this is a bond. And so I'm just twisting. Get your tetrahedral, your black, actually, get a blue or black ball and then just twist it into this orientation here. In fact, make oxygen blue this time. That way you can stick the lone pairs on there.
So is the dash the one with the back, and then the wedges are the
Yeah, the dash is going back
Okay.
and the wedge is coming out. I mean, that's usually. And so use black for carbon and blue for oxygen this time. And the blue for oxygen, put 2 short sticks and 2 long sticks. The 2 short sticks will be the lone pairs, the 2 long sticks will be the bonded atoms. And build this. You want to build it so the drawing, it matches the drawing. Now, it doesn't always match the drawing because we have free rotation, so this hydrogen's actually rotating. So what we're doing is we're freezing that hydrogen, and we're saying stop rotating. That way we can fix the position and flatten it into the plane so that we can draw it. Does that make sense?
Yes.
All right, when you do the model, make sure the H, C, O, H are flat. You got it? So you kind of twist it until it's flat. And then you'll see one of the H's pops out, the other H pops in, like that. What is the HCH angle? The HCH angle is going to be about 109. What is the HCO angle? I don't know why they didn't put HCO. There are 2 angles. There's the HCH angle and there's the HCO angle. So write in HCO on your page there. What is the HCO angle? Should be about 109. You know, they're all single bonds. How about the COH angle? The COH, now you got those two shorty lone pairs there pushing. And so the COH angle is going to be compressed. Each lone pair compresses at about 2 degrees, so this angle is going to be roughly 105. And so the angle is going to be about 105, so it's less than 109. The reason why we're coming up with a guesstimate is, you know, when you just say less than, you know, how much less than? Half? 5% less? 1% less? 0.1% less? We have no idea, so this is why we're just guesstimating the distortion based on other data. Uh-huh.
For O, will it have 3 sets or 4 sets?
O has 4 sets. 1 single bond, two single bonds, 3 would be a lone pair, 4 would be a lone pair. So we have 2 single bonds and 2 lone pairs. Lone pairs are taken separately. We don't combine 2 lone pairs into 1 set. So 4 sets. Do you see it?
Yeah, so that means it's
It's tetrahedral. It's tetrahedral EPG, but the MG is not tetrahedral. What is the MG? The MG is, you don't see the lone pairs. The MG is, you just look at the atoms. What does it look like? Bent. And so this is tetrahedral around this carbon, around this oxygen, it's bent. Okay, any other questions on that? Methanol? Okay, now we're going to go to glycine. With glycine, glycine is 2 organic groups in there. One organic group they call an amine. When we have this NH2, it's kind of like ammonia-like. An ammonia-like we call amines. It's going to have similar characteristics to ammonia. So it's NH. There's a nitrogen bonded to 2 hydrogens and a carbon. And then over here we have something called a COOH or CO2H. The COOH or CO2H is called a carboxylic acid. And so this is called an amino acid. Amino acids because it has an amine and an acid, all in the same molecule. Amines are base, so on the left side of that molecule is base. On the right side of the molecule is acid. They should react with each other, but they're on opposite sides of the molecule, so they can't. Sometimes they can if they're close enough. In this case, they're too far apart to react. It's one of those weird situations, but it's because of the structure. So let's take a look at drawing. Now, doing this using our procedure, the rules here gets mixed up because, you know, there's multiple central atoms. And so we need a little bit more information to help us draw the Lewis structures of these. And the little bit more information is, that's what we call a condensed structural formula. The condensed structural formula tries to draw out as is. And so what I'm going to do is I'm just going to keep track of the electrons to make sure I don't exceed. I have 1 nitrogen, which is 5. How many? 2, 4, 5 hydrogens, which is 5. 2 oxygens, which is 12. And 2 carbons, which will be 8. That's 25, 30. 30 electrons altogether. So I just want to make sure I don't exceed that, or I don't come up short. And so what I'm going to do is I'm going to put nitrogen here. It looks like the nitrogen is going to be bonded to how many hydrogens? 2. And then that nitrogen is going to be bonded to a carbon. And this carbon is going to be bonded to 2 hydrogens. And this carbon is also going to be bonded to a carbon because carbon likes to form 4 bonds. And this carbon is going to be bonded to an oxygen. And this oxygen is going to be bonded to an oxygen. And that oxygen is going to be bonded to a hydrogen. Is that right? Are amino acids explosive?
No.
You know, I see these at the supplement section, amino acids, but do you worry about them exploding like peroxides?
No.
You know, peroxides are oxidizers. They're good oxidizers. And ammonia or nitrogen is a good reducer. This would be like the, and so it's highly unlikely that we have a peroxide bond here, especially for amino acids. We don't really think of explosions in amino acids in the same thought. And so it turns out that it's impossible to draw a Lewis structure with an OH, an OO link. Instead, we're going to have to put the O over here, like that. And so what that means, CO2 means that we have two oxygens bonded to the carbon, like CH2. CH2 means we had two hydrogens bonded to the carbon, right? Okay, are we good with electrons? How many electrons have we used up? 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons. We still have a lot of electrons left over. If I have a lot of electrons left over, who gets them first? Oxygen or nitrogen?
Nitrogen.
No, oxygen gets them first. Why?
It's more electron.
It's more electronegative. Now, which oxygen gets them first? Bridging or terminal?
Bridging.
No. Sorry. Terminal. Terminal gets them first. Terminal gets them first. So let's complete the octet. And then who gets next? Who gets the electrons next? The oxygen. The bridging. Then who gets them next? Nitrogen or carbon? Nitrogen gets them next. And then who gets them? Carbon. Okay, now we have octets on everything, but let's make sure we didn't screw up the electron count. We should have 30 electrons. How many have we used so far? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. 32. 32 electrons. I used too many electrons. I only have 30 electrons. I used 32 electrons. So somebody has to lose electrons.
Carbon.
Who's going to have to sacrifice?
Carbon.
Carbon. Carbon's going to have to sacrifice. Now I have 30 electrons, except I have a problem. And what is that problem? Yeah, carbon doesn't have an octet. But you know what we could do is we could just convert a lone pair into a double bond, and that'll take care of it. And so which oxygen should I select to make a double bond with? The top one, right? Because if I select this one on the right, it's going to screw up all the formal charges. You recall that? And so the top one, we're going to take one and then bring it down into the bottom, like this. And now, does everything have an octet? What are the formal charges?
0, 0, 0, 2. N has -1.
Do you see a -1 somewhere?
No, that's. That one has N.
N?
Yeah.
Oh, let's count it. 1, 2, and then half of this is
Oh.
3,
I'm kidding then.
4,
Never mind.
5.
Yeah, that's good.
Yeah, that's good. Oh, actually, they're all 0. So this structure checks out. And in fact, this is the structure for glycine. This is the amino part. It's just like ammonia, except rather than having a hydrogen here, we have a carbon here.
Yes.
Carbon and hydrogen have about the same electronegativity. And so this is our base here. It's a weak base. This is the mean part, the amino part of the acid. This is the acid part over here. This looks like an alcohol, but it's different than an alcohol. What makes this different than an alcohol? What makes that different than an alcohol? Well, if we look at a typical alcohol, let's take ethanol, for example. take a look at this part versus this part here. Do you see the difference? This is an alcohol. This is what we call a carboxylic acid. Actually, let's look at an easier carboxylic acid.
The carboxylic acid has the double bond.
This is called a carboxylic acid. In fact, this one's called ethanoic acid or acetic acid. This one is called ethanol. This is an alcohol, this is an acid. What's the difference?
Has double bond. The O.
This one has a double bonded oxygen. What does that change? I'll tell you what it changes. Although we don't see it, because what are the formal charges? 0, 0. So we don't see the change in formal charge. You know where I see the change? I see the change in oxidation state. What is the oxidation state on this carbon here? Oxidation state, winner take all or 50-50 split? Winner take all. And so this carbon has, well, carbon versus hydrogen, who wins? Carbon, so that's 2. 4. Carbon versus carbon? It's a tie, unfortunately. So 2, 4, 5. Carbon versus oxygen? Oxygen, so 2, 4, 5, 0. 5 electrons. This carbon ends up with 5 electrons. How many did it contribute? 4, so it's going to be negative. How about this carbon here? Well, carbon versus carbon? Tie. So 1. Carbon versus oxygen?
Oxygen.
Carbon versus oxygen?
Oxygen.
So it ends up with 1 electron. How many did it contribute? 4. So the charge is going to be 3. Plus 3. Which means these two carbons are quite a bit different. This carbon is electron rich or electron poor?
Electron rich.
This carbon is electron
4.
poor. What happens is, if you have, what's the electronegativity of carbon? The electronegativity of carbon is 2.6. I think, is that right, 2.6? Yeah, in our book it's 2.6. In Chem 1A it's 2.5. But it doesn't matter. It just, the numbers are just rough anyway. And so here, it changes the electronegativity of the carbon. Which of these two carbons is more electronegative? The second one. That carbon is much more electronegative. Do you know what effect that has on the cloud? It sucks in the cloud much more strongly than this carbon. This carbon is kind of rich, so it doesn't suck in the cloud. If this carbon sucks in the cloud, it's going to start sucking in the cloud from the oxygen. But does oxygen like getting the cloud sucked? No. And so the net effect of that is the oxygen's unhappy. Therefore, it's going to suck the cloud from the hydrogen even more. When it sucks the cloud from the hydrogen even more, it makes this hydrogen much more positive. When we look at this hydrogen is much less positive. And so the degree of positive charge changes significantly here. And so when we think about acid, what is acid? Acid is H+. So the more positive the hydrogen is, the more acidic it is. And so ethanol, this is not really acidic. Not really acidic. In fact, we don't even consider it an acid. Don't really consider it an acid. We don't really consider it an acid because this hydrogen is not very acidic. Whereas this hydrogen is more acidic. This is an acidic hydrogen. you know, I'm being a bit ambiguous here. I say don't really, because if you have a powerful base, the powerful base will attack ethanol. Which hydrogen will it attack? Well, it's not going to attack any of these. It's going to attack this hydrogen. Now, let me ask you about acetic acid. Is acetic acid a tetraprotic acid or a monoprotic acid? How about these hydrogens? Are these hydrogens going to be attacked by the base?
No.
Well, let's take a look. What is the oxidation state? Actually, oxidation states, sorry, I don't circle. I put in parentheses. That way we can kind of keep track of it. Because the formal charges were circle, and so I screwed this up. I shouldn't have circled that. I should have just left it in parentheses. That way I don't get it mixed up with formal charges, because all the formal charges were zero and circle, right? And so here, what's the oxidation state on this carbon? Well, it's going to be a 2, 4, 6. Well, this is a tie, so 2, 4, 6, 7. How many did it contribute?
4 plus 3.
Not plus 3.
Minus 3, sorry.
Minus 3. Which means this carbon is electron rich. If this carbon is electron rich, is it going to suck the cloud away from the hydrogens here? No, not as much. I mean, it's slightly. In fact, we call them nonpolar, essentially. And so these are not acidic. These are non-acidic hydrogens. Non-acidic. This is acidic. So we don't consider this an alcohol. Alcohols are not acidic in general. This is an acid. This is an acid because of this oxygen. This oxygen changes the structure. All right, so the first thing we're going to do is the nitrogen. So how many sets are on nitrogen? 4. That would be 3 bonded atoms and 1 lone pair. What is the set geometry? Tetrahedral. So let's go ahead and draw that. So what I'm going to do here is I'm going to draw the nitrogen here, and I want the bridge to go down and right. This way I can keep writing this way. Because if I have the bridge go down and left, I'm going to run out of paper. And so we make the bridge go down and right. And so the bridge is going to go to carbon here. And then the terminals. I want as many terminal atoms here. So, well, I can only put 1. So let's put the hydrogen up here. And that means the other hydrogen's got to stick in or out. Which one do you want to make it? It doesn't matter. You want to make the other hydrogen stick in? Okay, if we make the other hydrogen stick in, then what's going to happen with the lone pair? It's going to stick out. And so let's go ahead and build this. We're going to use a blue one, and you're going to put 3 long sticks and 1 short stick. The short stick will be the lone pair. Then you'll put 2 whites and 1 black. And so go ahead and build that.
Do you want us to build the whole thing?
Okay, actually, before we build the whole thing, what is the molecular geometry? What is the molecular geometry? trigonal pyramidal. Trigonal pyramidal. Trigonal pyramidal is the molecular geometry. What is the ideal angle? 109.5. But the lone pair, remember the lone pair is that concentrated region of negative charge, and it's going to push the other ones down. Do you see how it's going to push it down? And so it's going to distort the angle, and so it's going to go from about 109 to about 107. 107. If I had two lone pairs, it would go down to 105. One lone pair is going to go down to 107. And so the angle is going to be about 107. And like that. Okay, then let's go on to this carbon. This carbon, how many sets? 4. How many bonded atoms? 4. How many lone pairs? 0. Okay, so that's going to result in what type of tetrahedral? Now, tetrahedral is going to have 2 in the plane. And so what I'm going to do is I'm going to put the bridge in the plane. And it's going to be a bridging carbon here. And then the terminals are going to stick out. One terminal is going to stick out like this. The other terminal is going to stick in like this. And so we'll put the hydrogens here. Do you see that? And so go ahead and build this portion of it. So this is for the first carbon. There's 4 sets, 4 bonded atoms, no lone pairs. The set geometry is tetrahedral. What is the ideal bond angle for tetrahedral?
109.
109. Okay, what is the molecular geometry of this? Geometry of the atoms around that carbon? Tetrahedral. And what do you estimate for the bond angle? About 109. They're all single bonds. They're all single bonds. They're going to be, even though they're different atoms, they're all single bonds. So just look at that. It says 109. All right, that's for the second carbon. I mean, the first carbon. Let's go to the second carbon here, which we'll label C2. The second carbon here. Has how many sets? 3 sets. 3 sets, 3 bonded atoms, no lone pairs. 1 double bond set and 2 single bond sets. What is the set geometry? Yeah, this one's going to be trigonal planar. And so now trigonal planar, we're going to try to draw all 3 sets in the plane. And so what I'm going to do is I'm going to put the double bond up like this and the single bond down like this. And so what we're going to use is we're going to use the brown one. Now the brown one has 5 holes. You have to use the brown one with the 3 holes in a trigonal planar arrangement. So we use a brown one for this. Brown one with 1 long stick and 1 short stick. The short stick will represent the double bond. The short stick is going to have a red ball. The long stick, actually let's use the blue. Let's use the blue balls for both oxygens.
You wanted blue for nitrogen.
I wanted blue for nitrogen, but we're going to have to use blue for this because the reds, they didn't drill any holes in the reds. You could use a red here, that's fine. But I want you to use a blue for this oxygen. All right, so where are we at now? So we have the set geometry, trigonal planar. What's the ideal angle here? 120. What is the molecular geometry? So the set geometry is trigonal planar, but the atom geometry, does it match? Is the atom geometry the same as the set or group geometry? Yes, it is. And so the molecular geometry is also trigonal planar. So it's trigonal planar, set, and group, or molecular. Except the angles are going to be distorted. The angles are going to be distorted because of the double bond. And so what we have is this. The OCC angle. Take a look at the OCC angle should be bigger than 120 or smaller than 120?
Smaller.
Okay, what we have is the double bond is concentrated negative charge here. We got concentrated negative charge is going to push these other two away. And so that means that this angle is going to grow. So this is going to be greater than 120. This one's going to shrink. How about this one here? This one's going to grow too. So this is going to be greater than 120. This is going to be less than 120. Do you see the reason why? It's because of that double bond. The double bond needs more space. The double bond needs more space. It's going to push these other two bonds away from it. And so what we say is about 2-degree distortion. So this should be about 118, 118. This should be about 116. I mean 122, 122, 116. Does that make sense? All right, now these two lone pairs, I'm not going to try to draw 3D out. We'll just have that, get the two lone pairs there. Those two lone pairs are actually in the plane of the board because that oxygen, this oxygen is also what? The set geometry for this oxygen. Trigonal planar. So everything's in the plane. The double bond and the two lone pairs are in the plane. However, this oxygen is not. What is this oxygen here? This oxygen, how many sets? 4 sets. If it has 4 sets, it's going to give it what set geometry? Tetrahedral. So what I'm going to do is I'm going to try to put the bonds in the plane here. And that means I have the bond to the hydrogen here. Or no, yeah, that's right. And then that means one is going to stick out. And that's going to be a lone pair. And one lone pair sticks in. Like that. So what you're going to do is you're going to twist this oxygen until we have this. These atoms should all be in the plane. H, N, C, C, O, O, H. Those should be flat in the plane. Do you see it? And so twist it until everything's flat, like this. That means that this H sticks out, these two H's, and these lone pairs here, this lone pair. Can you visualize it on paper as well as in the model? Does the model match the paper? Yeah? Good. All right. Did you guys bring your data from the last week's experiment? Yeah. Did you guys calculate the molarity? No. Does everybody have their data? Yeah. All right. Let's. Do you want to finish that lab now? We'll continue this lab only in class, or do you want to continue Lewis? Well, we got the models. Yeah, we should continue the Lewis. Checking out the models is a hassle. All right, let's continue the Lewis. I skipped nitrite, so let's go back to nitrite. I skipped carbonyl fluoride. Nitrite's a tough one. Sulfur dioxide is tough. let's do carbonyl we'll do carbonyl fluoride and then we'll do nitrite. COF2, carbonyl fluoride. So this is a simpler one. A simpler one, we don't have to use a lot of extra knowledge to do. So carbon's 4, oxygen 6, 2 fluorines. Fluorine is 7, so 2 of them will make 14, no charge. So this is going to give us 24 electrons total. What should we throw in the center? Carbon. So we'll have a carbon to an oxygen to 2 fluorines. Something like that. But, you know, carbon's still shy of an octet, but let's complete the octets to the others. So we've used 6 electrons so far. 2, 4, 6 of the 24. So who's going to get the electrons first? Fluorine or oxygen?
Fluorine.
Which one's more electronegative? Fluorine. So let's go with fluorine first. 2, 4, 6. 2, 4, 6. And then oxygen. 2, 4, 6. So now you know how many electrons have we used up? 2, 4, 6, 8. 8 times 3 is 24. 24 electrons we used up. So we're good. Except we're not good because carbon doesn't have an octet. So who's going to sacrifice their electrons to give carbon an octet? Oxygen or fluorine? Oxygen. In fact, the rule is fluorine will never sacrifice its electrons. Fluorine will absolutely refuse to do a double bond. And so what we're going to do is we're going to take 2 electrons off the oxygen and place those in the bond, like so. Okay, now everybody has an octet. How are we doing with formal charges? Yeah, this top oxygen, 2, 4, 5, 6. That's good. The carbon?
2, 4, that's
That's
good.
good. Fluorine?
4, 6, 7, that's good.
Yeah, so this structure checks out. In fact, this is the structure. This is the structure. And so when we look at it, what is the number of sets? 3, 0. Set geometry? Trigonal, planar, with an angle, 120. The molecular geometry? Trigonal planar as well. Except the angles are going to be distorted. Which one takes up more space? Double bond or single bond? Double bond. So what it's going to do is it's going to push these 2 out and these in. And so this will be about 122, 122. So OCF, 122. OCF, about 122. And the FCF, about 116. So it has to add up to 360. Now, I'm not going to get too fancy about the lone pairs. On the oxygen, these 2 lone pairs are actually in the plane because this oxygen is trigonal planar as well. It's got 3 sets. However, the fluorines are not. The fluorines are what? How many sets do the fluorines have? 4 sets. 4 sets is what geometry? Tetrahedral. So 1 lone pair is in the plane, 1 lone pair sticks out, the other lone pair sticks in. Do you see that? But you know, we aren't going to bother getting that fancy. We're just going to leave it like that. And so rather than drawing out the lone pairs, which is going to get kind of messy, we'll just draw them standard like this without showing geometry. And so this would be the shape. the molecular geometry drawing. All right, now let's go to nitrite next. Nitrite, nitrogen, 5, 2 oxygens, 12, and a -1 is 1. So this is going to give us 18 electrons to work with. For nitrite, what do you want to put in the center? Nitrogen. So let's go N with 2 oxygens. That's good. Okay, then let's fill in the electrons. So far we used 4, 6, 8, 10, 12, 14, 16, 18. So it gives us our 18 electrons there. Does this look good? No. The problem is oxygen. Or, no, the problem is nitrogen. What's wrong with nitrogen? Octet. And so, who's going to sacrifice? Oxygen 1 or oxygen 2? Does it matter? No. So let's pick oxygen 1. If oxygen 1 sacrifices, we end up with this structure. Now we have an octet, but what are the formal charges? Well, this one has a, negative. We need a negative because the whole thing has to be -1. It's an ion. But why did we pick oxygen 1? Why didn't we pick oxygen 2? Was there a reason? No, there was no reason. It's just, in fact, we could have picked oxygen 2 and we would have generated this. We would have generated, had we picked oxygen 2, we would have generated this structure. These are called resonance forms. Resonance forms. We use a double-headed arrow. Double-headed arrow indicates resonance forms. Double-headed arrow for resonance. I'm not going to bother with the hybrid. Remember, the hybrid's the average. We're just going to draw the resonance forms. When we do shapes, molecular geometry, we just pick one resonance form and analyze that. So which one do you want to pick, the left one or the right one? I guess it doesn't really matter. Right? Left one. Okay, so we're looking at nitrogen here. So nitrogen is the central atom. How many sets? 3 sets. 2 bonded atoms, 1 lone pair. What is the set geometry? Trigonal planar. And so what we'll do is let's do this. I'll put the lone pair on the top here, and then 1 bonded atom I'll put down here, and the other bonded atom I'll put down here, like that. Okay, what is the ideal bond angle? 120. What is the molecular geometry? Bent.
Is it bent with a D?
Yeah, B is in Bravo. Bent. Bent or angular? Bent is a lot shorter to write, so just write bent. The ideal angle is 120, but what do you expect the ONO angle to be? Well, this double bond should compress it, but this lone pair should compress it the opposite way, so I'd expect it to be about the same, 120. And so it should be about 120. The one's going to compress it down, the other's going to compress it up, so it kind of cancels each other out. All right, you know what? This one I don't think you need to build, right?
No.
No. So we need time to, you have to reorganize the model kit so it looks like the picture on the inside cover. And so can you spend some time getting it organized? And then just return it. And then we'll just call it a day.